Welcome back. This is the second part of my multiple linear regression tutorial. If you haven't watched the first part, then please go and watch it, because this is based on that and things will make much more sense if you watch that video first. In the last video we finished by trying to quantify how good and how significant a model is, and in this video we'll start with trying to quantify how significant the coefficients are. Remember, we said that the idea now is to find the values of those p's, b0, b1, b2 all the way to bp, and now we're trying to quantify how significant the values of b's are. Now, if the regression model is significantly good, then we can use the t-test. I have a tutorial on data exploration and analysis. In there I speak about the t-test. You can watch that tutorial if you want. Now we use the t-test to estimate the statistical significance of each coefficient. So for each coefficient we want to check the statistical significance. The significance test, or the t-test, t to n minus p minus 1 equals bi, and all those equations. You can see that SE now is standard error of estimation is the square root of SSE over n minus p minus 1, and the degree of freedom is n minus p minus 1. As you can see here, these are just straightforward equations. We can plug in the values and get the results. Now SSE is the sum of squared error, as we explained in previous videos. Now there's something called multicollinearity, and it can be a problem in multiple linear regression. Why is that? A high degree of multicollinearity between predictors produces unreliable regression coefficient estimates. So if there is a high degree of multicollinearity between predictors, we have a problem, and that can result in having unreliable coefficient estimates. We want to check for signs of multicollinearity, and these include high correlation between pairs of predictive variables, or the features. So remember that we said before we can compute correlation between them, and if there is high correlation, then that's a sign of multicollinearity. Regression coefficients whose signs or magnitudes do not make good physical sense. We can use our experience. Statistically non-significant regression coefficients are unimportant predictors, or extreme sensitivity of sign or magnitude of regression coefficients to insertion or deletion of a predictor. So if it's very sensitive, if things are very sensitive when we add or remove a predictor, then that is a sign of multicollinearity. And usually when we compute the covariance matrix, as we explained in the previous video, covariance matrix for the x variables, for the input variables, then the diagonal values in the inverse of that matrix are called the variance inflation factors, or VIFs, and they are very useful in terms of measuring multicollinearity. So if any VIF, if any of those diagonal values in that matrix, the inverse of the covariance matrix of the input variables, if any value in the diagonal value in that array exceeds 5, then multicollinearity is there, and we need to address it. We have the problem. The next point is model selection. So a frequent problem in data mining is to avoid predictors that do not contribute significantly to a model prediction. Maybe we have a lot of features and many of them don't contribute much to the model prediction. We need to address this problem. First, it has been shown that dropping predictors that have insignificant coefficients can reduce the average of error predictions. So if we have predictors or features which don't contribute much, then we need to remove them, and that can actually improve the accuracy. Second, estimation of regression coefficients are likely to be unstable due to multicollinearity in models with many variables. Again, multicollinearity can be there if we have too many variables. Finally, a simpler model is a better model with more insight into the influence of predictors in models. So if the model is simple, we don't have too many predictors, then that's a good model. It's usually better, and that gives us more insight into the influence of predictors in the model. And there are two ways or two main methods for model selection. Forward selection, the best predictors are entered in the model one by one, so every time we can add a new predictor or new feature. And the opposite way is the backward elimination. The worst predictors are eliminated from the model one by one. So if we have, let's say, 20 predictors or 20 models, we can either start by adding one each time and checking the performance, or we can remove one by each time and check the performance. Now the last part of this video is an example of multiple linear progression. You can go to Professor Said's website and then go to this page, mlr.htm, and you will find a link there to an XLS file. I use LibreOffice, and you can open this if you have a LibreOffice Calc, or you can use Microsoft Excel. And here we have dataset, 3 variables, x1, x2, x3, and the output variable, and we can use it to build the matrices that we spoke about in the last video. Now let me enlarge this because we have a lot of calculations here on the sides. As you can see here, we can compute the covariance matrix, and then the inverse of that covariance matrix for the input variables and for the output variable, if you remember from the last video. And then the correlation matrix as well. Remember we spoke about correlation in the check for multicolinearity, and then we can compute all the other statistics that we spoke about, to the T statistics and things like that, and then we just find the values or the array of the coefficients. You can just, if you're familiar with Microsoft Excel, then this should be very easy for you to play about with, basically. Yes, just go there and download the file, and imagine that you have only x1, x2, x3 and y, and then you can build these values and these columns. Y prime, for example, is the predicted value, E is the error, E hat 2 is the squared error. So if you click on the cell, you can see that it says G2 squared, and G2 is this, and G2 is E2 minus F2. So the error here, this value minus this value, so that's and that, and it's this value minus this value. Anyway, I hope that makes sense. If you're familiar with Microsoft Excel, then that shouldn't be a problem for you to understand. Thank you very much for watching. I'm going to stop here, and I'll see you in my next video.